Welcome to the lesson on power systems. Upon completion of this lesson, learners will be able to distinguish between AC and DC power systems, name the main types of motors used in robotics, including their working principles, name the main components of AC and DC motors, and name and describe other types of motors used in robotics. To begin, here is a high-level overview of the different motor types. Electric motors can be categorized into two main types: alternating current, abbreviated as AC, direct current, abbreviated as DC, and other classifications. AC motors include induction and synchronous types. DC motors are further divided into separately excited, self-excited, which includes shunt, series, and compound subtypes, and permanent magnet varieties. The other classifications category includes stepper, brushless, servo, and universal motors. Each type has specific applications and characteristics suited for different industrial and commercial uses. Note that industrial robots work mostly with the combination of several different types of motors. The robot could utilize various motor types, including AC motors, DC motors, servo motors, stepper motors, or linear motors. Linear motors, specifically, often involve another type of motor connected to a linear drive mechanism to produce linear motion. These motors can be used in combination. For example, a robot might employ all DC motors, or it could use an AC motor for one component and DC motors for others, or even utilize all servos or all steppers. We will discuss each motor type individually, exploring their construction, components, and applications. The panel image here provides a high-level overview depicting an electrical panel with two motors attached. The panel illustrates the various electrical components that connect to the motors. It includes power input, safety components such as switches that shut off power in case of excessive current, control devices such as ladder logic or programmable logic controller at the top, and safety features like emergency stop buttons. Finally, the controller or computer that drives individual motors is also part of the system. At the bottom, you can see the two motors, which could be AC, DC, or a combination of both, connected via wiring. Let's begin with alternating current motors, also known as AC motors. AC motors power heavy-duty industrial robots and material handling tasks. They are used in high-power applications that need consistent torque. These motors are common in industrial-scale operations and supporting systems. They need less maintenance since they have no brushes or commutators. AC motor robots can plug directly into wall outlets, making them practical for industrial use. Let's look at the key components of an AC motor. They are the armature, rotor, stator, and windings. Labeled here as number 1, the armature typically carries the current and interacts with the magnetic field. It is a part of the rotor. Number 2 is the rotor. It is the rotating part of the motor. It interacts with the stator's magnetic field. Number 3 is the stator. It is the stationary part that creates a magnetic field. It contains the windings responsible for generating the rotating magnetic field. Finally, we have the windings, labeled as number 4. The winding refers to the coils of wire. Windings are present in the stator. Now let's look at the two types of AC motors, starting with synchronous motors. Synchronous motors are characterized by their distinct feature where the rotor rotates at synchronous speed, aligning perfectly with the rotating magnetic field. One notable limitation is that larger synchronous motors cannot self-start due to their high inertia, requiring auxiliary starting methods. These motors use either separately energized DC rotor windings or permanent magnets for operation. While the universal motor represents a single-phase synchronous design, it's the three-phase synchronous motors that have earned the title workhorses of industry due to their robust performance and reliability in industrial applications. These motors are particularly valued in heavy manufacturing and large-scale industrial processes where consistent speed and high power output are essential requirements. The next type of AC motor is the induction motor. In contrast to synchronous motors, induction motors operate at a slightly slower speed. The rotor's rotational speed is always slightly less than the speed of the rotating stator field. This difference in speed is known as slip. The rotor of an induction motor typically consists of a squirrel cage design, essentially a cage-like structure with embedded windings. Unlike synchronous motors, the rotor windings do not receive external power. Instead, the current flowing through the stator windings induces a current in the rotor windings. This induced current then creates the rotor's magnetic field, which attempts to synchronize with the rotating stator field. However, complete synchronization is never achieved, resulting in the characteristic slip. It's important to note that single-phase induction motors require an external starting mechanism. Now, let us shift the focus to direct current motors. Direct current motors, also known as DC motors, utilize direct current instead of alternating current. The power source can be a battery or a converted AC current. DC motors are widely used in industrial robotics due to their ease of speed and direction control. In contrast to AC motors, where speed control involves adjusting the frequency of the alternating current, DC motor speed is controlled by simply increasing or decreasing the current flow. Reversing the direction of current flow reverses the motor's direction. DC motors also exhibit rapid acceleration, reaching full speed quickly. However, DC motors can be more susceptible to external load variations, which may affect their speed. Despite this, DC motors are prevalent in robotics due to the widespread availability of DC power. They are often used to drive the base motors of robotic arms, which require significant force and must support substantial mass, such as the base, shoulder, and elbow joints. Here are the main components of a DC motor: the armature, commutator, brushes, and poles as depicted in the image. Number 1. The armature is a rotating coil of wire within an electric motor. Number 2. The commutator is a segmented copper sleeve located at the end of the armature. Number 3. The brushes are carbon pieces that ride on the commutator. Number 4. The poles are the magnetic poles inside the housing, representing north and south. To briefly review how a DC motor functions, let's consider the interaction between the field windings housed in the stator and the armature winding on the rotor. For simplicity, let's assume that the stator has a permanent magnetic field. When direct current flows through the armature loop, it induces a magnetic field that attempts to align with the stator's magnetic field. To maintain continuous rotation, the direction of the magnetic field within the coil must constantly change. This is achieved through the commutator, which, in conjunction with the brushes, reverses the current flow in the armature windings as the rotor rotates. This continuous switching of the armature's magnetic field polarity ensures that the rotor constantly seeks alignment with the stator's field, driving continuous rotation. The ease of speed control in DC motors stems from the ability to regulate the strength of the magnetic field in the rotor by simply adjusting the current flowing through it. DC motors come in 3 distinct mounting configurations, each designed for specific applications. Series wound motors are suitable for high torque applications where speed regulation is not a critical factor. Also known as universal motors due to their ability to operate on both AC and DC power, they are commonly found in portable tools. Shunt or parallel wound motors are predominantly used in industrial applications and represent the most common type of DC motor, particularly suitable for variable speed machine tools. The compound wound configuration combines the characteristics of both series and shunt windings, offering high torque capabilities with good speed regulation. While more expensive than the other configurations, compound wound motors are ideal for specialized applications such as presses or reciprocating machines, where both power and precise control are required. So now that we've looked at AC and DC motors separately, we're going to do a quick review of some of the differences for each type of motor. AC motors, powered by alternating current, are characterized by their brushless design. This brushless construction contributes to their longer lifespan and lower maintenance requirements. Speed control in AC motors is primarily achieved by varying the frequency of current. Their repair costs are relatively economical. In contrast, DC motors operate on direct current and incorporate brushes in their design. These brushes require more frequent maintenance to sustain operation. Their speed is controlled through adjustments to the armature current or field windings. DC motors typically incur higher repair costs compared to their AC counterparts. Let's discuss a few more key differences between AC and DC motors. AC motors typically utilize 9 wires plus a ground connection, while DC motors generally operate with 3 wires plus a ground. When it comes to power supply, AC motors have the advantage of not requiring current conversion, whereas DC motors need conversion systems, such as converting AC to DC power. AC motors excel in applications where power performance is the primary requirement, while DC motors are preferred in situations where precise speed control is essential. In terms of phase configuration, AC motors can be either single-phase or 3-phase, while DC motors are commonly single-phase. Another significant distinction lies in their armature operation. AC motors typically feature stationary armatures with a continuously rotating magnetic field, while DC motors can have either rotating or stationary armatures. There are other types of motors such as servo, stepper, universal, and brushless DC motors. In this lesson, we will focus on servo motors and stepper motors. Let's begin with servo motors. Servo motors are renowned for their precise position and velocity control and are the most common type used in industrial robots. This precision is achieved through an integrated feedback system that monitors the motor's output, including its position and rotational speed. This feedback loop allows for fine-grained control. Feedback mechanisms can include Hall effect sensors, which utilize electromagnets to detect rotating magnetic fields, or optical encoders, which use gaps in a disc to track rotational position and speed. They are widely used in low-power applications, such as small and miniature robotics and mobile robots. Servo motors typically operate on DC power, aligning with the power requirements of many robotic systems. Let's now look at stepper motors. Stepper motors provide precise position control by rotating in fixed angular steps, making them ideal for applications requiring exact movements such as 3D printers, CNC machines, and pick-and-place robots. These motors offer high torque at low speeds and can maintain position without requiring feedback sensors, making them cost-effective for automated assembly lines and packaging systems. In industrial robotics, stepper motors are commonly used for end effector control, conveyor systems, and precision positioning tables, where accurate incremental movement is critical. While stepper motors excel in precision control, they have limitations such as resonance issues at certain speeds and reduced torque at higher speeds, which must be considered during system design. Stepper motors are typically more expensive than servo motors. This diagram illustrates the operating principle of a stepper motor. Stepper motors achieve precise position and velocity control by utilizing a series of discrete electrical pulses. These pulses sequentially energize different sets of stator windings, creating a rotating magnetic field. The rotor, in response, aligns with each successive magnetic field generated by the stator windings. While the diagram shows only 6 stator windings, practical stepper motors typically have more, allowing for finer position control with a smaller number of input signals. By precisely controlling the timing and sequence of these electrical pulses, we can accurately control both the position and velocity of the motor. Faster pulse rates result in faster motor rotation while maintaining positional accuracy. Stepper motors require specialized controllers to generate the necessary pulse sequences. However, such controllers are readily available and often integrated with the stepper motor itself. One significant advantage of stepper motors is their efficiency. Once the motor reaches the desired position, it can maintain that position without continuous current flow. In contrast, DC motors, including servos, require continuous current to maintain position and must counteract momentum to decelerate. This inherent holding capability of stepper motors makes them energy efficient. Here's a list of various motor types and their specific applications in robotics for EV manufacturing processes. Induction motors are primarily used for powertrain assembly, heavy lifting operations, and conveyor systems throughout the facility. Synchronous motors handle large press operations, stamping machines, and high-power processes that require consistent performance. DC motors are employed in battery assembly, component handling, and testing equipment where speed control is important. Servo motors specialize in precise tasks such as battery cell placement, robot joint movements, and quality inspection procedures. Stepper motors are utilized for small part placement, tool positioning, and conveyor indexing, where exact incremental movements are needed. In summary, robotic systems are powered by 2 types of electric energy sources: alternating current and direct current. The electrical motors used in robotics can be configured with different winding arrangements, series, parallel, or compound, each suited for specific applications. Beyond these basic configurations, there are specialized categories of electric motors, including servo, stepper, brushless, and universal types. Among these various options, servo motors are the most widely used choice in industrial robots due to their precise control capabilities and reliability. Thank you.